So now I'll start covering, we've covered the arithmetic instructions so far, and some of the inline barrel shifter feature, and things like that. So this, we'll start talking about how we can move data around. This doesn't cover memory operations yet, but there are two instructions that you need to know for moving data from one register to another, and that's MOV and MVN. And what MOV does is, just like it says, it just moves the value in one register into another register. Now there are variations on this. One of them is the move T, which just moves the top half word of the 32-bit value into the destination register. And then there is the move as PC. So this is a special instruction because you're changing the program counter. You're telling it to do a branch at this point. So you're actually taking an instruction address, loading it into PC, and telling it to actually branch to that instruction that's been updated in the PC. Now the other side effect of this is you can see that there's an S flag, and this one is a special instruction because it actually changes the mode as well. So we'll cover a little bit about the different modes. But if you're in user mode, like we've been talking about so far, and you do a move as PCLR, it will switch back to the, it will take the value that was in the SPSR, which was the save program status register of whatever mode you were in, and then update the mode to, in the CPSR to the current mode. So we'll use this instruction with interrupts especially because whenever an interrupt occurs, like an IRQ or an FIQ exception, the ARM changes mode to that to the IRQ or FIQ mode, and it actually takes a copy of the CPSR and puts it into the SPSR for you automatically. But it's our responsibility to take the SPSR and move it back into the CPSR, and so this is sort of a one instruction to do all that in one go essentially. So we'll cover that in more detail later. Finally, we have MVN, which is the move negative. It takes the negative one's complement of the value in the register and puts it into the destination register. Now, these instructions cannot be used on memory and are only applicable to registers. So again, getting back to that load store feature of ARM. So here's some instructions. This was an interesting example because I tried to multiply two constants and it calculated the answer directly for me and generated assembly to do the same. So here you can see it's actually taking this large value, trying to multiply by 3, but it's actually just loading the value directly into the register. So here in this case, the 2 million, so this large value down here, get the mouse, there it is. So this large value, once you multiply by 3, you get another large value, but it's moving the entire word with a bogus top half word, and then followed by moving the actual 2797 piece afterwards. So for some reason, it's decided to optimize this way. It might not be what you intended for it to do, but that's what it does. So it's just good to know. So here it's moving the lower half word value with a bogus upper half word value, and then finally it replaces that upper half word value with 2797 for your final answer.
Is there no move lower half only?
There is. So we'll cover that a little bit later. So there's actually, you can do it up to the byte. So you can do byte moves, you can do half word moves, or you can do the 32-bit. Here's another one. But this time we have, we're trying to subtract a really large value from a variable. And so it, again, the way it optimizes for these constants is it loads these by using move W, move top, right? And loads the loads them half word at a time, and then does the operation. The other interesting thing I wanted to show you is I was able to get the CPSR value to actually update on this one with the negative. So the trick was to read the APSR, which is the Application Program Status Register, which is a synonym for the CPSR. So these are changes that happened post like ARM v5. So if you look in the example, in the folder example 6, you'll actually see some assembly, inline assembly to read these CPSR values, and I just found it useful. So the next one is how do we do reversing byte order? So sometimes we're all in little endian mode. We store data in different endian mode, and we don't want to use ARM's hardware features to access that memory. Well, this is how you do it. So ARM does all these hardware level optimizations for memory access, but it's better just to stick with one convention, which is little endian. And then if we want to do our own little big endian operation, you can do it in code using RAV, which reverses the byte order and endianness of the value in the register. Reverse 16 just does half word at a time, reversing the byte order. And then finally, I believe reverse SH, it does it for only the lower 16 bits. And it also updates, it does a sign extension, which means if you have a negative value, it treats the lower half word as a 2's complement integer and extends the sign when it does the operation. So here's an example. So if you have reverse R0, R0, and R0 is filled with A, B, C, D, D, E, FF, then it does it as FF, D, E, C, D, A, B. So it takes, goes basically in reverse byte order and puts that into R0. Similarly, reverse 16, it'll keep the, it'll just take A, B, C, D and reverse those, and then it'll take FF, D, E and reverse those. So this is reverse 16. So if you were to use reverse SH, it just takes these and flips these two on them. Does that make sense? So I just wanted to put this in again. This is the illustrious current program status register with your flags. So the reason I put it in is for these logical operations, which come next. So this is just for your reference. Again, I just put it in there every time, so people don't have to, or they can look it up at the board. Also, I've written them there. So now we get to logical operations. So you have the AND, which does a bitwise AND of the two operands, stores it into the destination register. Bitwise clear, you provided a mask, and wherever there's a bit that's set to 1, it clears that bit to 0. Exclusive OR does the exclusive OR of two operands, stores it into the destination register. ORR is the instruction for bitwise OR, and similarly, bitwise OR not, which takes the one's complement of the second register, and then bitwise ORs it with the first one and stores the result into the destination register. Compare is interesting because all these logical operations actually end up updating your flags. So that's how they figure out whether a logical operation was true or false, is they do it using the flags. So compare, for example, takes the two operands, and you're trying to compare if it's greater than or equals and things like that. It'll actually subtract the two values and then update the appropriate flags, and that's how it does the comparison. So similarly for compare negative, which is a misnomer, there is no real negative, it's just adding the two values in the registers and then setting the flags. Now these two instructions, there is no destination register, so it's just going to either add the two values and then update the flags, and there's going to be no update to a destination register. So you only have two operands for these instructions. TEQ is similar to exclusive OR. Instead of doing an add and a subtract, now you can do an exclusive OR with two register values, and it updates the flags for equality using an exclusive OR. And finally, the test does an AND. And we'll look at conditional execution a little bit later. That's where these will be useful. So you can actually do a branch based on the logical operation preceding it. So here's an example of AND. And you'll almost always see an AND with an S for updating the flags. And it only takes two operands. Same thing with bitwise OR. And so here you can actually see it's only it's always using an S suffix with the instruction. This one's interesting because here the compare instruction that was generated. So here I have an if condition where I'm taking a exclusive OR of two variables and then checking if the result is greater than 0. So that actually translates into the exclusive OR instruction above, where it takes the two variables, does an exclusive OR, and then it does a comparison to 0. And if it's less than or equal, this is sort of the conditional execution that I was telling you guys about. And based on the earlier logical operations, it's able to decide whether to branch to back to main or back to or whether to go to the add function or subtract function. So these are actually offsets from main to add and subtract. So bitwise clear. So here, again, as I had mentioned earlier, it takes the bits that have been set to 1 and clears them. So what it's doing essentially is it's taking the ones complement of the one operand and then ANDing it with the second operand register and storing the result into destination. So the mask can be a shifted value as well. So here I'm just using a simple example for bit clear R2, R0, R1, but you can also provide a logical shift operation on top of this last operand, and you can do some more complex things. And this is especially useful because a lot of ARM uses memory mapped I/O, and you want to be able to set interrupt bits or disable interrupts and things like that. So bit clear comes in very handy for this. So now we'll talk about memory operations. So far, most of the instructions we've covered don't generally touch the memory as much. So the load and store operations are what allow you to get data from memory into the registers and then store them back. So one of the caveats that I found from the manual was that the load store can only load and store data on the boundary alignment that is the same as the data type being used in the program. Load can only, an example of this is load can only load 32-bit values on a memory address that's 4-byte aligned. But you can also do things like half-word aligned memory accesses. And if you want to deal with 64 bits, you actually have to translate that into two 32-bit moves. So an example here is, so when you say LDR R0, R1 in brackets, so what the bracket stands for, you can think of as memory contents of. So you're taking the memory contents of the address that's stored in R1 and putting that value into R0. Okay. Similarly, store goes in the reverse direction. Now you'll notice, if you remember, I had mentioned that the destination register comes first. But in this case, the destination is really memory. So when you say store R0, R1 in brackets, what it's doing is taking the value in register R0 and storing it at the address that's stored in R1. So it's going the opposite direction. LDR, and you can have interesting variations on this same instruction by doing immediate value additions. You can also do shifts using the inline barrel shifter on the same instruction. So for example, LDR R0 with R1, 4 means that take the value or the memory contents of the address in R1, add 4 bytes to it, take the value at that address and store that into R0. And similarly, store does the exact same thing, but in reverse. So it takes the value in R0 and stores it into the value into the address at R1 plus 4. So this square bracket notation is actually called pre-indexed addressing mode. So there are different addressing modes that we'll look at later, where if you want to update the value in R1 here, for example, you can do that. So instead of just accessing that memory location and then leaving the address in R1 alone, you can actually update it. So it's like it becomes like a plus equals sort of. And we'll look at that later too. So here's an example. So here I actually used a pointer, an integer pointer, to actually get it to generate the store and load instructions. So here I'm adding to the pointer value after assigning it the address of a local variable. And here, what you actually see, we'll talk a little bit more about frames in ARM, but it's taking the stack pointer, which is always stored in R7. It acts as your base pointer or your frame pointer, generally in thumb mode. And it's taking the values off the stack, which is where your local variables are being stored, plus 4 and plus 12, and then actually storing and loading from that memory address. So as I mentioned earlier, R7 is known as the base address register, and the base address register is different from the base pointer that I had mentioned. So the base address register we'll refer to that terminology when we do load store multiples, but it's the register that contains the base address of where you want to perform that memory operation, like the load or the store. And the base address register can be anywhere from R0 to R12, the stack pointer, or the link register. So you can do load stores on stack pointer, you can do load stores on R0 through R12. You can even do it on the link register, which is your saved program count. And so we'll cover that in more detail later. Now we get to control flow operations. So far we've covered arithmetic operations, data moving operations, logical operations, memory operations. So how do we get it to do interesting things by using branching? So a branch is exactly that. It takes the value of your subroutine address and puts that into the PC. So if you write to the PC or the program counter, it actually turns into a branch, and it actually jumps to that address. Now, I mentioned to you the two different modes in ARM, which is the thumb and the ARM mode. So you actually have limits on, because of the encoding, of the instruction, you have limits on how far you can jump with branch. So with a branch, you have a range of plus or minus 16 megabytes from where your program counter currently is in thumb mode. And in ARM mode, you have 32 megabytes. And that makes sense because you have a 32 bits for your encoding versus 16 bits for the same instruction. Similarly, branch with link, BLX is an interesting instruction because it actually saves the program counter into the link register before jumping to the target address. So it does this for you. So that's the BLX. So, and BX will do the same thing. So the X is essentially specifying, store the program counter into the link register and then jump to the new program counter value. And similarly, you have a compare and branch. So this allows you to do a comparison operation and a branch in one instruction. Earlier you saw examples where you did a conditional branch, but you had to do a logical operation beforehand, and then do a comparison or an exclusive OR, and then do a jump separately in a separate branch instruction. This is more for code size optimization, I guess, that they've included this. But as you can see, the range is also very limited with the compare and branch to 0, where you can only jump either +4 or +130, because the PC is always pointing 2 instructions ahead. In thumb mode, you're going to be able to do +4, jump to the 4 instructions ahead, or you can go up to 130 bytes ahead in the address space. And you also have a table branch where you can have an offset-like table, and you can tell it to use the value in that table for the branch. So TBB does just that, and so you're limited sort of on the size here again to 510 bytes for the offset. This is what you can store in your offset table, not the offset table size itself. Similarly, TBH is with half-word offsets, so where you just want to manipulate the lower half-word, you can jump from 0 to about 131 megs. So we had seen an example of this before. I thought I'd go into a little bit more detail on how these conditional branches work. So earlier we had seen a branch if less than or equal, so that's what BLE stands for. All it's doing is, based on the logical operations that have occurred before this, it's updated the negative, 0, or overflow flags, and it uses those 3 flags to say, check whether it was less than or equal or not. So here in this case, if it's equal, generally the compare operation does a subtraction. So it'll set the 0 flag if the 2 values were equal and it subtracted them. The 0 flag gets set, so it knows, hey, it's a equals condition. And the overflow and negative flags are compared if it's less than or greater than, essentially. So those are the 2 differences. So that's how it's able to tell whether it's whether it's a branch if less than or branch if greater than. And if equal, again, it just uses the 0 flag, and not equals also uses the 0 flag. It only branches if the Z flag is set to 0. So as I've explained, it's using the negative and the overflow flags to check if the values are greater or less than. So here's an example. This is an example in your examples folder. So I'm actually trying to do a loop, I believe. So it's actually comparing 2 values and then branching if the comparison is not equal. So actually a for loop, if you think about it, it just has a I is less than or I is equal to something, keep looping. So that's what this is doing. Here it's actually jumping to a libc function if the 2 values are not equal. So, and you can see this is another example of how arithmetic shifts or logical shifts are being used in line with a move. This is again for your reference. So having covered all these arithmetic operations, logical, memory operations, and sort of the conditional branching operations or control flow operations, we can actually look at hello world. And this is actually on your VM. So if you guys go to the hello world folder in your projects directory, should already have had your emulator up and running. If not, it should be in your slide book. How to bring that up. If you go to examples and then hello. So let me just walk through sort of what's happening in assembly. So these are the instructions beginning with a dot are actually assembler directives, which tell the assembler sort of how to arrange these objects and sort of to identify the different pieces in the code. So in here we have a global start, which is similar to your main method. And so this is how the operating system knows where to start executing your program. The way you actually do system calls in assembly is you use the syscall number is actually loaded into R7, and then you do a SWI instruction. So this is one of the first instructions that you'll see for changing mode. So SWI actually stands for software and interrupt, and all it does is it changes your processor from user mode, which is what we've been talking about so far, where all your programs run, into supervisor mode. So normally the Linux kernel will be run in supervisor mode, and it has privileged accesses to memory and things like that as compared to user mode. And it can do a lot more things in supervisor mode. So the way to switch to supervisor mode is actually to use the SWI instruction, or recently they've been deprecating SWI and coming out with something called the supervisor call, which is SVC instruction. So you can use either SVC or SWI. And you just, the way you pass the argument to the system call to specify which system call it is use R7. So in this case, you can see I'm setting R7 to 4 for syswrite system call. And I'm setting the file descriptor to 1, which stands for std out. The message, actually, you can specify using a ASCII Z directive for the assembler, which says this is just a string. Place it somewhere in read-only memory, and whenever you say message colon here, can't really see that very well. Makes it tiny, but it's actually message. So whenever you reference message, it refers to the address of this string, essentially. And so you're loading the file descriptor as the first argument to your syswrite call, followed by your string's address. Finally, you pass it the length of the string. So in this case, it's 14 characters, including the new line. And then you move the syswrite number, which is 4. There's actually online, you can find plenty of references for syscall numbers, and then you just call SWI, and it makes the system call. It switches to supervisor mode, kernel takes over, sees that it's trying to run a syswrite system call, runs the system call, and then comes back. And then all I do is a similar thing, but for sysexit, to exit the code. So if you guys actually run make, it'll generate the hello world executable, and then you type hello, and it prints hello world to the screen. So, and if you look at the make file, so here you can see I'm not using GCC as the compiler for the assembly code. I'm using the GNU assembler, which is called by using AS. And then I have a separate linker, which is actually, I believe it's called Gold, GNU linker. So that's LD. And so it takes the assembly file, generates the objects, and then generates the, and then links it for running in memory, and then generates the executable in ELF format, ELF. So one of the interesting things about the SWI syscall is the encoding that's generated from the SWI instruction. It actually only uses the 8 bits for the encoding, I believe. So you have 24 bits that are still available that you can actually use, and we'll look into that a little bit later. So you can differentiate between different SWI system calls. And for some reason, the Linux kernel that's running here doesn't use those 24 bits. So you can see it says SWI 0. So it actually appends that value to the encoding. And so here, Linux just ignores it. But you could actually use it to differentiate between different system calls. So when you say SWI1, it could mean, or SWI4, it could mean syswrite versus a SWI1, which would mean system exit. So I don't know why they didn't do that, but that's just the way Linaro chose to implement it. So the instructions we've covered so far are up there. So we went sort of through the arithmetic operations, logical operations, memory, data operations. Finally, we went through control flow, how the branches work, and finally we covered the SWI as used for a system call. So all the SWI is doing is it's changing the mode and running the interrupt handler for the software interrupt. And the Linux kernel is using that for its system call convention. So now we get to an exciting and fun lab called, it's the Fibonacci sequence number generator. So the idea is you're going to write in assembly. I've given you some filler code to start off with, and sort of the algorithm to how to do this. But this will hopefully help you in writing the assembly code for this. So you have, it's basically exactly what a Fibonacci sequence is. So for the interesting value to look for will be 6, because when you enter a 6, you should get an 8. The rest of them are pretty much the same. So X is sort of your index variable. And actually there were 2 sample algorithms that I found for this. So there's one that does it recursively and one that doesn't. And for the assembly one, I figured it would be shorter to use the recursive algorithm. So the assembly filler code that you're seeing is actually using this algorithm here. So if you have a different one that you'd like to implement, please let me know. So the file that you'll be modifying is fib.s, which is the assembly file. The fib.c is just a shell for calling the function as a main. It just calls Fibonacci. Yeah. And one of the things that I haven't mentioned yet is that the way you do return values in subroutines is to put the value into R0. So R0 becomes your return value for a function. All right, so this is actually a possible solution. This is not the solution. So just like the recursive algorithm that was shown earlier, first thing to do is we compare to see if the value is less than or equal to 0. So x gets passed into us in register R0. So we'll see this a little bit more in detail later, but ARM's calling convention for calling methods is to pass the arguments to a method in the registers R0, 1, 2, and 3. It doesn't use the stack like you've seen in x86. So there's a certain calling convention when you call methods in ARM. So what it's doing here first is it's saving R3, R4, R5 and the link register onto the stack so that it can mess with the values, right? And before it exits out of the function, it actually restores it using a pop. So this was sort of the first instructions that we covered, was the push and the pop. So it's just pushing all these register values and saving them so it can use R3, R4 for other operations, and then popping them off the stack before it returns. And if you look, the way it returns is actually to pop the value into the program counter, thereby causing a branch back to the calling function. In this case, it was main. So the first thing the recursive algorithm showed was to do a comparison of the index with 0, see if it's less than or equal, and to return 0 if it is, and otherwise return a 1 if it's equal to 1. So that's exactly what we do here. So here it's actually using something called labels. This should have been provided for you. So when you say a .L3, it actually refers to the instruction address down here. So it's just a sort of labeling in assembly. I'm sure you've seen this before. So first thing it's doing here, interestingly, I did what Benjamin had suggested from the remote site, which was to write the code in C, generate the assembly, cheat a little bit, just to see what would be produced. So as you can see, instead of doing a comparison operation, it's doing a direct subtraction, which is what a compare actually is. But it's updating the flags in the process, right, using a sub S. So it's comparing the index being passed in to the value 0, and if it's less than or equal, then it jumps to L3, where it actually sets the return value, which is also passed using R0 to 0, and then it's returning by restoring the stack and the program counter. So when it entered the method, it saved the link register onto the stack, which is where the calling method is coming from. That the main's address is stored in the link register, so it saves that on the stack, and when it returns, it restores that link register back into the PC, and the program counter now points back to main, and it's back where it called Fibonacci. Does that make sense? So we'll get more in detail into calling convention a little bit later. So once it's compared to 0, and then it's compared to see if it's equal to 1, it goes to either of these two where it returns a 0 or a 1. Okay, so this is sort of exactly what we saw with these two C statements right here. So this jumps to a .L3 label, this jumps to .L4 label, right, and returns 0 or 1 accordingly. So that's what these two are. And finally, the recursive portion of this, which is interesting, is it actually adds a really large value, which is FFFFFF, which in 2's complement notation is a -1. So in order to subtract 1, it chose to add this really large value constant to R4. And if you see here, R4 actually has the value of R0 stored in it. So the index value X is being stored in R4 like a variable, and it's being used here to subtract 1 and then return, do a recursive return. And similarly, when it wants to subtract 2, So it's passing the index value here to Fibonacci. So R0 becomes the first argument to Fibonacci here as well as here. So all it's doing is it's taking the local variable for which is a copy of x, subtracting 1, calling Fibonacci, and then subtracting 2, calling Fibonacci again. Now, finally, after the recursive call is made, it actually does add the two values. So here, from this branch, you'll get a value in R0, and from this one, you'll get a value in R5. It adds the two, stores that in R0, and then returns the value. Does that make sense? So this is where it's adding the return values from the two Fibonacci recursive calls. So the interesting thing to note here is that you get the return value in R0 here, and it saves that value into R5 before it makes this next recursive call, right? So hopefully everyone was able to get this.